I welcome you back to our course on machine learning using Python. So today we are going to look at an important issue of variance in linear regression and how you can control that. So you might want to revise your bias variance trade-off concept, which we'll cover a little bit, and you may also look at your concepts on linear regression. Okay, so let's get started and see what we have today. So we'll look at the bias variance trade-off. We'll look at how do we do subset selection to reduce variance. Again, how do we do ridge, lasso and elastic net for the same purpose. So that's the overall plan. Now, let us understand the concept of bias and variance once more. So essentially, if you remember, that the models also have tendency like human being, that they try to memorize stuff rather than trying to understand the concept. They will memorize. So what do you do in this case? You don't give him the final question set, right? So you give him a question set to practice, which you call it as training set, okay? And then you keep a separate set to evaluate his concepts, which is called as the testing set, all right? So, and this training set and testing set are from the observations which you are creating by random samples. So, the samples can vary from one person to another person. Are you with me? All right. Now, what do you want your model to have a characteristic like? So you want that when you build your model on different samples, okay, you want the predictions to be as close as actual, right? For all the models that you build on different samples. If such a thing happens, then you call your model to have a low bias. Also, what you want is that you don't want your models to really memorize your training data. So you do not want your parameters to be too much dependent on the data, right? Every nitty gritty, every small change, you don't want it to remember. You want it to understand the overall concepts, right? So if such a thing happens, or that is what you want, then the variation in the model parameters, right? The variation in the model parameters should not be very high from one model to another model. When such a characteristics is exhibited, you call such a model to have low variance. It turns out that total error has two components. One is your bias and another is your variance. All right. So let's look at a graph, and you see total error is actually summation of bias and variance. You might be wondering why this bias square. It's very simple. Variance is in square terms, bias is in linear terms. So you just square bias so that both are in similar units. All right. Now, as you increase your model complexity, so you have more levers to go closer to the actual value. So that reduces your bias, right? And however, as you have a lot of parameters, your models can vary a lot, right? So that gives you high variance as you increase model complexity. And you want somewhere to pick a model here which has an optimal model complexity which minimizes your total errors, right? So that's what is your objective. Let us understand further. Okay, let's say you have these red points over here and this green line is your model, all right? So if this happens, then you call this is overfitting, because if you change some points from these training observations, this line will completely change, because you see it is following the data completely, right? So this memorization problem. Okay, now if you come here, what happens is that this is underfitting. Underfitting meaning it is not understanding any pattern of the data. So you change any of the training observations, the model is not going to change, and it is far from the actual value, so it has a high bias. And finally, you want maybe something like this, okay, where the variance is also low and the bias is also low. So low bias plus low variance is your high performing model. Now, a question might be that linear regression is a simple model, right? It's not a complex model. So why do I worry about variance over here? I can give you two scenarios. First scenario is that your training data set is very small, inadequate, okay? Extreme case, you have just 2 points, right? And if you have one variable, right, your you can fit a straight line which goes through these 2 points, right? So even if linear regression is not a model which overfits, in this case it will make the model go through these points, right? So that is one scenario. The second scenario can be when your n is comparable to p. What is n? N is your number of training observations. What is P? P is your number of independent variables. Okay? You may wonder, does it happen in real life? Of course, if you take data from, you take gene expression data, you have different patients, maybe 30, 40 patients. For them, you have maybe 8,000 to 9,000 gene expressions. So your gene expressions is your independent variable and your patients are your observations, and you may want to find out what is the patient's condition, right? On respect to a disease, all right? So these are two scenarios. So what can we do? The first thing is we can select some attributes, some features from the set of independent variables. Okay. So such a technique you call as subset selection. The second technique is called as regularization. Okay. Let's look at them one by one. So in subset selection, we are going to look at two methods. One is called as a best feature set method. So what you do over here is you follow a very simple trend, okay? So let's say you have a data set with 4 features, F1, F2, F3 and F4 and a target variable. Now what you do is you build a model with no features and you find the residual sum of square. You remember, or you can try to find out the minimized square error, right? So you always want your error to be as less as possible, right? So maybe you build a null model, all right, where you get your MSE as 550, okay? So you want to reduce it further. In your next step, you build 4 models, okay? How do you get 4? You get 4 by 4 choose 1, 4C1. So you are building actually all possible models of one feature from a set of 4 features. And you calculate your TMSE or training MSE. So from here, you see that for F2, you have got the minimum MSE, which is 350. I go to my next step where I increase the features from 1 to 2. How many models I will build? I will again build 4 choose 2 models. 4 into 3 by 2, which gives you 6 models. And in every step, I am keeping a note which was the best model with 1 feature, which is the best model for 2 feature, like that. I go ahead and build with 3 features, 4 choose 1, 4 models, and I get M, F1, F3, F4 to have the lowest training MSE. And finally, with 4 features, I have only 1 model with a MSE of 100. So I select these 4 features now. So this was on training MSE. Now I am going to look at the test MSE, all right? And so that I can differentiate the term, I have denoted testing MSE as VMSE or validation set MSE. Okay, so let's calculate that. Once we do that, we see that MF2 is 370, MF2F3 is 180, MF1 F3 F4 is 150, and MF1 F2 F3 F4 is 170. Can you make out why we are evaluating only these 4 models? Because we have selected the best model with each feature count possible. So we have taken best M1, best M2, best M3 and best M4. Okay. So finally we say that F1, F3, F4 is my best model and I have reduced 1 feature. So for 4 features, the reduction doesn't look much, but if you think of a percentage scale, you have actually removed 25% of the features. Okay. So in a formal way, this can be written as you start with M0, which contains no predictors, then you vary k from 1 to p. P is your number of independent variables, and in each step you calculate CP1 models, okay, or rather PCK models, right? So final model you will have exactly k predictors, and in every step you take the best model, right? So that's how you get your p number of models, okay? And what is happening over here, how do you select? You can select by smallest RSS like mean square error, or you can take largest R square. Then once you have that, you can use these best models, cross-validate that, and pick the best among them. So there are some alternative measures like Mallows CP, AIC, BIC, or adjusted R square. Okay, so these things you can read up. These are just alternative techniques of using your mean square error. Our next technique is going to be forward stepwise. Okay, so what we do over here is we have similarly training phase and testing phase. In training phase, we start by building models using one feature at a time. How many models we'll get? We'll get 4 C1 models. So these are the training MSE that we have got, and we select the one with minimum MSE, right? So MF2. Then we don't consider any other model. We just want to expand this model which has F2 already included. How I can extend? I can extend by 3 ways, okay, where I include all other features. So if I extend, I see F1, F2 to have MSE of 200, F2, F3 to have MSE of 150, and F2, F4 to have MSE 250. Now what do I do is, I again choose the best. So I select this one. Now I have two features. I will add more features here. And when I add more features, this F2, F3 is fixed, right? We are not going back on that. Okay. So I have option of adding only two features now, F4 and F1. I calculate them and find out that M, F2, F3, F4 is best among three features. And finally, you have all the feature models. Okay. So like last time, we have taken the ones which are best for each feature count, right? So finally, you are getting 4 models here as well, okay? And you then find out the validating MSE just like the other case, and you see that F2, F3, F4 is your best model as far validating MSE is there. Now your question might be that this looks very similar, right? What's the difference? So the difference is that if you remember when we looked at the training MSE, we evaluated all possible models. So here we have included all possible models, or 4 choose 3 models, or 4 models, whereas here we have only evaluated 2 models. Okay, and if you see, the results are also not same, right? So here we have got F2, F3, F4, okay, but in last case we might have got something else, like we got F1, F3, F4, okay. So what is happening? Why should we go for forward stepwise? The answer to this is that if you have 10 features, imagine how many number of models will be there in your best stepwise. First step you have 10C1, second step 10C2, this way you go. So 10C1 plus 10C2 up to 10C0 will give you 2 to the raise 10 minus 1, or 1023 models only with 10 features. If you increase your feature set, number of models will increase exponentially, right? So that is not something you can do. So that's why you will go for forward stepwise. Similar to forward stepwise, you have backward stepwise, where you start by including all the features and then you remove one feature and see where your MSE is getting reduced, and that's how you proceed. Okay, so both are valid techniques. Let's look at the algorithmic form. So we start with M0 model, okay, and then we move from k equal to 0 to p minus 1, and each step the number of models that we are constructing is going down. So if you go back here, you see initially we have made 4 models, then 3, then 2, finally 1. So that's what this is telling, that every step will make p minus k models where k varies from 0 to p minus 1. Then choose the best among them, alright, for each feature count, and finally you validate using your validation test MSE. As I said, this Mallows CP, AIC, BIC, these are also very standard measures which you can read up and find more about. Okay. Now, let's look at the other aspect of regularization. So we'll start by looking at Ridge. Okay. So Ridge, if you remember, linear regression tries to minimize this residual sum of squares. Okay. And this is your loss function. This indicates how good your model fits your data. And as I said, to regularize, what you do is, apart from your data fitment part, you add a regularizing term. Okay. So what is this regularizing term doing here? So if you add a term over here, you can understand that basically you are adding some bias to the model. Okay. But why would you do that? So we will understand that slowly. And please see, the lambda will be greater than equal to 0, which is a tuning parameter. If lambda equal to 0, what will happen? This will become your simple linear regression problem again. So let's understand this further. Okay. So let's look at effect of lambda. When lambda equal to 0, this is your linear regression line. Okay. When lambda equal to 10, this green line is your model. When lambda is 100, then this red line is your model. Okay. So what do you think is your model of lambda doing? So lambda is actually reducing slope of your line. Okay. Why do you want to do that? So basically you want your model to be less sensitive to input data. What it will give, what benefit it will give you. So if you have less training data, you will not blindly start following your training data. Okay. So that is the advantage that you are trying to find out. And of course, if you make lambda very, very big, then it will be completely underfit, very high bias model. Okay. So let's look at some characteristics of this model. So the testing set, as I said, may be very small, and in that case linear regression will follow closely the points. As I said, if you have just 2 points, the line will go through it. The penalty term adds bias, right? So you are more far from your actual value. However, you hope to reduce variance because it doesn't fit your small training data anymore. This penalized loss function to be used on training set, not on testing set. And finally, this is very, very affected by the scaling. All right. So you actually perform scaling and then you apply this model. Okay. So that's the basic idea. Now, this is an example for your ISLR book. Basically, what you are trying to do is, these are your different features. As you have a value of lambda equal to 0, these are your linear regression coefficients. As your lambda increases, it goes very close to 0. And if you have a very, very high value, that will be completely high bias system, completely underfitted system. You may note that this is also called as shrinkage. Okay, so it takes value close to 0 but not to 0, and as you use a squared form, okay, so you remember that a vector's magnitude, so this you can think as a vector, and a vector's magnitude is often referred as norm. As you are taking the squared values to find the norm, you often call this as L2 norm. Okay, so this is about ridge regression. All right, now let's look at the bias, variance and total error in context to Ridge. So again, as you increase this lambda, you see your bias is not going up very highly. Okay, so your bias is rising only after you have a high lambda value, but it has a dramatic effect on reducing the variance. Okay, so that's what is the philosophy of Ridge, that you play around with your lambda with minimal effect of bias but take down the variance by a lot. Okay, why variance will come down? Because as you are reducing the coefficient, they are becoming less and less sensitive to the inner variability between the samples on input data. Okay. All right. Now let's go to Lasso. So Ridge has one problem, right? That it includes all P predictors in the final model, right? So the coefficient goes down, but actually it doesn't remove the features, okay? Remove the variables. So there is another technique called as Lasso. So they are principally very simple or similar. That apart from the loss function that we have, we'll add a penalized term. However, Lasso adds a different penalizing term. It takes the absolute value, and again you have a parameter called as lambda. So this is actually your L1 norm. Okay. If you look at the effect of coefficient here, same effect you will see that when lambda is 0, it is like linear regression. Coefficients are having high value. However, as we increase lambda, you see some coefficients are becoming 0. Okay. So Lasso is not only a shrinkage model, but it also acts as a variable selection model. That's why it is also called as a sparse model. Okay. So now let's try to understand at a very high level why Lasso can remove some variables and Ridge cannot. Okay, don't worry too much about this graph. This may look complicated. So essentially what you assume is you have two features, and beta 1 and beta 2 are your coefficients. Okay, and what this blue region indicates. So if you remember, for Ridge regression you are taking a square, right? And you want the square of beta 1 square and beta 2 square to have some constant value, right? So you don't want that penalty to be more than that, right? So actually, that gives a circular shape, right? Circular shape of your constraint or your budget, all right? Whereas in case of a Lasso, it gives a shape like a diamond, okay? So it has sharp angles, all right? And what these contours indicate. So basically, you cannot represent your loss function with respect to beta 1 and beta 2 because that needs a three-dimensional plot. So for that you use contour plots. So what contour plots do is that each of these contours have same RSS, okay? Each of these contours have same RSS, and as it goes up, right, as it increases, the RSS are going up. Okay, and you want to find out that where this contour actually intersects this budget. Okay, so as it is a circle, now the chances are very less that it can cut somewhere on the axis, because if it cuts somewhere on the axis, then actually you can have your coefficient value to be 0. Whereas in this case, as these diagonals have very sharp angles, the circles can cut them over the axis and you can have some coefficients as 0. So this is at a very high level the concept why for Lasso some of the coefficients can be 0. So this turns out that as you increase number of features, you will see that as you increase number of features, lot of coefficients will hit this sharp edges and it will go to 0. Now what we go to is another variation, okay, which is called as elastic net. So in elastic net, what happens is that this large p and small n case, right, high dimensional data with few examples, Lasso selects at most n variables before it saturates. Okay, so it will select n, it will not select less than that, right? So it will saturate before that. You may want to go much lesser than n features. And if there is a group of highly correlated variables, right, so then Lasso tends to select only one variable from a group and ignore the others. So this is one of the problems with Lasso. So it kinds of feels that it's like both of world, right? So we want something which takes some feature of Ridge and some feature of Lasso. So that's what elastic net does. Elastic net has a form where there is a penalty term in terms of Ridge, L2 norm, and also a penalty terms in terms of Lasso or L1 norm. And you can understand that this is a generalization. When lambda is 0, this is ridge regression, and when lambda 2 is 0, then it is lasso. Okay, so in this lecture we try to give you the basic ideas on specific scenarios why you need to reduce variation of or variance of linear regression model. And there are two techniques as we discussed. One was subset selection and another was regularization. Please go through this and give your questions. We'll try to get back to you and answer as much as we can.